Dear students, now we discuss application of Laplace transform in solving differential equations. Solving differential equations using Laplace transform. Now first we see procedure and then we discuss some examples. First step is take Laplace transform of given differential equation to obtain an algebraic equation. Usually a polynomial equation. Simplify this equation to obtain equation of the form, say capital Y of P equal to some function of P, where capital Y is Laplace transform of small y. Small y is dependent variable in the differential equation. And find inverse Laplace transform. So that you will get y of x is equal to some function of x, which is a required solution. Let us solve some examples. Example 1. So, solve the initial value problem. Initial value problem is a differential equation with given initial conditions. Y double dash plus y dash minus 2y equal to 0, y of 0 equal to 1, y dash 0 equal to 3. Okay, so this is differential equation, and these conditions y of 0 equal to 1, y dash 0 equal to 3, these are called initial conditions. So this problem is called as initial value problem. So given differential equation is y double dash plus y dash minus 2y equal to 0. We take Laplace transform of this equation. Before that, we write the formula for Laplace transform of derivatives. So we have Laplace transform of second order derivative, that is y double dash. It is, by definition, it is p square into Laplace transform of y minus p into y of 0 plus sorry, it is minus y dash 0. Now we know y of 0 and y dash 0. These are given things. Y of 0 is 1, y dash 0 is 3. So this is equal to p square. Now L of y, we call it as capital Y. Capital Y, which is function of p, minus p into y of 0. Y of 0 is 1, minus y dash 0. Y dash 0 is 3. Okay. We call this as 2. Equation 2. Then we also have L of y dash. It is given by p into L of y minus y of 0. That is equal to p into y of p minus y of 0. Y of 0 is 1. So this is number 3. We substitute 2 and 3 in the Laplace transform of 1. Okay. So taking Laplace transform of 1, and using 2 and 3, we get. So what is Laplace transform of given differential equation? Laplace transform is linear, so L of this thing is L of y double dash plus L of y dash minus 2 times L of y equal to L of 0 is 0. It is a linear operator. L of y double dash minus plus L of y dash minus 2 times L of y is equal to 0. Now we use 2 and 3. From 2, L of y double dash is p square y of p minus p minus 3. P square y of p minus p minus 3 plus L of y dash. It is p into y of p minus 1 minus 2 times L of y is y of p equal to 0. Now we simplify this for capital Y of p. Okay. So we have p square plus p minus 2 into y of p. We take other terms to write. So we get minus p minus 3 minus 1. So it is minus p minus 4, which now becomes p plus 4 equal to p plus 4. Okay, therefore y of p equal to p plus 4 divided by p square plus p minus 2. Okay, now we have to find inverse Laplace transform of this term on right side, but it is not simpler. We have to simplify right hand side using partial fractions, as we already have seen. Okay, so first we factorize this term p square plus p minus 2. Okay, so this is p plus 4 divided by, this is p square plus p minus 2. It is p minus 1 into p plus 2. And now we try to write down this as a divided by p minus 1 plus b divided by p plus 2. Okay, then we multiply this thing by p minus 1 into p plus 2, so that we get p plus 4 equal to a into p plus 2 plus b into p minus 1. Then we substitute particular values of p. Especially we are interested in p equal to 1 and p equal to minus 2. And then we get values of a and b. Okay, so this is partial fractions. Okay, so this is 5 by 3 divided by p minus 1 minus 2 by 3 divided by p plus 2. Okay, and now we are ready to take inverse Laplace transform. Okay, taking inverse Laplace transform, we get y of x. Y of x means L inverse of y of p, which is equal to L inverse of right hand side. Again, L inverse is also linear operator, so this is 5 by 3 L inverse of 1 upon p minus 1 minus 2 by 3 L inverse of 1 upon p plus 2. Now we know a Laplace transform of e raised to at is 1 upon p minus a. So L inverse of 1 upon p minus a is L of e raised to x. Okay, sorry, it is not t, it should be x. Laplace transform of e raised to ax is 1 upon p minus a. So L inverse of 1 upon p minus a is e raised to ax. So this is 5 by 3 e raised to a is 1 here, so it is e raised to x minus 2 by 3 e raised to a is minus 2 here. Okay, so p minus a, so a should be minus 2. Okay, so this is required solution. Now we solve non-homogeneous differential equation. That means right hand side is non-zero. Next example. It is y double dash plus omega square y equal to cos of 2x. Here omega is constant and omega square such that omega square is not equal to 4. Here initial conditions are given. Y of 0 is 1, y dash 0 is 0. Let us solve. Okay, so first we write the expressions for Laplace transform of y double dash and Laplace transform of cos of 2x. Okay, we have, so let us call this differential equation as 1. Now we have Laplace transform of y double dash is p square L of y minus p into y of 0 minus y dash 0. This is p square L of y is capital Y of p minus p into y of 0. Y of 0 is 1, so it is p, and y dash 0 is 0, so next term will not be there. Okay, now Laplace transform of cos 2x. is and Laplace transform of cos 2x. We know Laplace transform of cos ax, it is p divided by p square plus a square. So this is p divided by p square plus a is 2. So this is 2 square, that is 4. Okay. Now we take Laplace transform of differential equation 1 and use these two things. So let us call this as 2 and this as 3. Taking Laplace transform of 1 and using 2 and 3, we get L of y double dash plus omega square, omega is constant, omega square L of y equal to L of cos of 2x. Okay, now substitute the values. L of y double dash is p square capital Y minus p square y of p minus p plus omega square L of y is y of p equal to L of cos of x is cos of 2x is p divided by p square plus 4. Okay, so therefore p square plus omega square into y of p equal to p divided by p square plus 4, and this minus p we add in both sides so that it is plus p. Now we simplify this for y of p and we can write y of p equal to p divided by p square plus 4 p square plus omega square plus p divided by p square plus omega square. Okay. Now we simplify this using partial fractions as usual, but note that denominator terms are p square plus 4, p square plus omega square. So we need to write AP plus B of this form. Okay. So to simplify this, we use partial fractions. That means p divided by p square plus 4 into p square plus omega square. We write it as AP plus B divided by P square plus 4 plus CP plus D divided by P square plus omega square. Then we multiply this equation by P square plus 4 into P square plus omega square. And then we take particular values of P and we try to find the values of A, B, C, and D as usual. Here we get this as 1 upon omega square minus 4 into P divided by P square plus 4 minus P divided by P square plus omega square. Okay. So we substitute in the right hand side of capital Y of P, simplify again, and we write therefore Y of P equal to 1 upon omega square minus 4 into p divided by p square plus 4 plus 5 minus omega square divided by omega square minus 4 into p divided by p square plus omega square. Okay, note that omega square is not equal to 4, so this is valid thing. Okay, in the denominator we have omega square minus 4. Okay, now we are ready to take inverse Laplace transform. Okay, so taking inverse Laplace transform, we get y of x, which is nothing but L inverse of capital Y of p, which is equal to L inverse of right hand side. By linearity, it is simply 1 upon omega square minus 4 into L inverse of p divided by p square plus 4 plus this constant 5 minus omega square upon omega square minus 4 L inverse of p divided by p square plus omega square. And we know that this is in terms of cosine. So 1 upon omega square minus 4. This is, we know Laplace transform of cos of 2x is p upon p square plus 4. So this is cos 2x and second term plus this constant 5 minus omega square upon omega square minus 4 into L inverse of p divided by p square plus omega square. Of course, it is cos of omega x. Okay, so this is required solution of given differential equation. Okay. Thank you.